On the 28th of May 2024, the Norwegian Climate Realists had invited to a lecture with the title "What Humans Contribute to Climate Change?" This video is a composition of this lecture with a few additional explanations. Everywhere we are faced with the request, "Stop global warming." And then the question, what have you done to protect our climate? People may give different answers like this here. My answer is simple. I have tried to better understand climate impacts and to search for the truth. So, to give an answer to this headline, it is good first to look to the climate of the past and the main native impacts. Then I'll briefly look to the IPCC's interpretation of the climate change before more closely discussing an alternative approach, in particular the carbon cycle, and a few remarks about the general impact of CO2 and the sun on our climate. About the very first 4 billion years of the Earth's history, we don't know too much. But since the Cambrian 570 million years ago, first information from proxies can be derived. From the 018 to 016 ratio in sediments, proxies allow to reproduce temperatures, here displayed as red graph, which were varying over more than 10 degrees and were almost 10 degrees higher than today. Over 4/5 of this period we had so-called warm ages and only over 1/5 ice ages. To make this clear, an ice age exists when one or both pole caps are covered by ice, so there is no doubt we are living in an ice age, the so-called Quaternary. Therefore, it's a bit strange that with 1/2 or 1 degrees more we already could reach a tipping point with disastrous consequences for our planet. From proxies we also know that the CO2 concentration varied over almost 6,000 ppm, that is 6 per mil, and over the Cambrian era it was 15 times higher than today. We see no real correlation between temperatures and CO2, but we know that with a concentration of 400 ppm or 0.4 per mil, we are at the lower end for the photosynthesis of plants and therefore the existence of life. So, what brought about these dramatic temperature changes? One of the most dominant and long-time changes are known as Milankovitch cycles, which consider the Earth as a gyro with its different degrees of freedom spinning around the Sun. One effect is that the Earth's rotation axis is precessing with a cycle of about 26,000 years relative to the orbit. At the same time, the axis tilt is varying over 41,000 years, known as obliquity, and the orbit is rotating as perihelion rotation with 112,000 years around the Sun. Together this causes a modulation of the solar irradiation of 19 to 24,000 years. Further, we have a changing eccentricity over 100,000 years. This means a variation of the longer to the shorter axis of the ellipse, which causes a changing intensity on Earth up to 23%. And also the position of the gyro axis to the shorter or longer distance to the Sun brings about a difference between the hemispheres of up to 28%. At the same time, the Sun is not fixed, but shows an inertial motion around the barycenter, the mass center of the solar system. This motion is mainly affected by the largest planets Jupiter, Saturn, Neptune, and Uranus. It additionally modulates the eccentricity with a period of about 2100 years. So there are different impacts caused by the constellation of the Earth to the Sun. Let us briefly look with higher resolution to the last 4,000 years of the Holocene, the interglacial area of our ice age in which we are living. From ice cores on Greenland, for example, we have a temperature reconstruction relative to the local annual mean temperature. We see 300 to 600 years long warmer periods with fast changes up to 2 degrees and total variations over 3 degrees. The overall trend can be influenced by the Milankovitch cycles, but not the fast oscillations and particularly not the steeper slopes. A possible trigger for these rapid changes is seen in the global conveyor belt or thermohaline circulation, which is driven by temperature differences and salinity. Warm water from the equator is carried towards the poles on ocean surface currents and moderates the climate in the north and south. When it is cooled, the salty water sinks to the bottom of the ocean, where it is pulled again towards the equator. This sets up a global oceanic conveyor belt, which also dissolves and transports a lot of CO2 to the bottom and appears thousands of years later again at the equator. It consists of the Atlantic meridional overturning circulation and for the other half the Southern Ocean overturning circulation with more or less periodic oscillations of the subsystems, which are known as Atlantic multidecadal oscillation and the Pacific decadal oscillation. They are different to the El Niño Southern Oscillation, which appears irregularly in intervals of 2 to 7 years. For example, the Atlantic multidecadal oscillation, as recorded over 170 years, turns up with periods of 50 to 70 years. These temperature fluctuations are caused by changing ocean currents and swelling deep water. They are explained by a natural fluctuation in the climate system. One possible reason is the periodic constellation of the great planets of our solar system with increasing gravitational forces on the Sun and the Earth, as this has closely been discussed, for example, by Nicola Scafetta and Jan-Erik Solheim. In this context, also another important impact should be mentioned: the variations of the solar activity. Since Galileo Galilei and his observations of the sunspots on the surface of the Sun, there was always the speculation that these spots and also the faculae could be an indication of the solar activity. The sunspot number periodically oscillates with a period of 11 years, the so-called Schwabe cycle, and is caused by a reswitching of the solar magnetic field from one direction to the opposite. Also, longer cycles of a few hundred years can be observed. The total solar irradiance only varies by about 1 per mil. But the varying solar magnetic field has a direct impact on the incident cosmic radiation from outer galaxies, shown here as the upper blue graph with a phase difference of 180 degrees. Via a chain of different processes, this radiation, now shown as brown graph here, generates condensation nuclei for the cloud formation, which is displayed here in blue. So, with increasing solar activity, the cosmic flux is reduced and results in a lower cloud cover. This solar-induced cloud feedback can amplify the solar anomaly by a factor of 3 to 5, as this has been discussed and investigated by Henrik Svensmark and collaborators in many contributions since 1998. Since the Little Ice Age, the temperature increased over the last 150 years by about 1 centigrade. This is slightly dependent how far the urbanic influence is correctly homogenized. Rural areas only show an increase of 0.5 centigrades. The stronger modulation of 50 to 70 years here fits quite well with the AMO, while there is little correlation with the monotonically increasing CO2 concentration. Large-scale satellite measurements exist since 1978. The steeper increase since 1980 corresponds to an incline of slightly more than 100 centigrades per year. This has to be compared with temperature differences between climate zones of more than 180 degrees, and also differences over the seasons at one location of about 100 centigrades. So, we are talking about changes of 1/10,000th of the temperature differences on Earth over the year, and this with year-to-year variations of about 2 centigrades, which are 200 times larger than the mean increase of the 100 centigrades per year. But with the inception of the industrial era, for many climate scientists and in first position for the IPCC, natural impacts no longer exist. Instead, they claim only human-emitted fossil fuels are responsible for an increasing CO2 concentration in the atmosphere. And second, more than 90% of the temperature increase is caused by this greenhouse gas. We have to look closer to these claims and to face them to own explanations. I'll start with a brief review of the IPCC interpretation of the carbon cycle. They assume before 1850 the carbon cycle was in balance with an atmospheric concentration of about 280 ppm and with an in and out flux of approximately 80 ppm per year. Over the industrial era, so the IPCC, this cycle has come out of balance with about 410 ppm as average over the last 10 years, and with an additional flux of 26 ppm per year only caused by fossil fuels and land uptake. Actually, human emissions increased to 4.8% of the total emissions, from which slightly more than 50% are directly absorbed by the oceans and land. The rest, the so-called airborne fraction AF, with about 46%, cumulates in the atmosphere. This is made responsible for the rapidly rising CO2 concentration over the industrial era with about 130 ppm. The removal of this additional CO2 from the atmosphere is expected to take up to a few 100,000 years and is described by different adjustment times tau A. On the other hand, the residence time tau R as ratio of the concentration to the total emission or absorption is only 3.8 years. So, what IPCC assumes is summarized by this sketch. Note also the 130 ppm allegedly caused by humans are circulating with this residence time and almost forever remain in the atmosphere. At the same time, more than 50% of the new anthropogenic emissions are directly sequestered and the other part accumulated in the atmosphere. So the respective balance takes this form. The incident human emissions are reduced by the absorbed part, and the concentration is increasing with the airborne fraction. Year-to-year summation gives the rising concentration over time as magenta graph here, which is in good agreement with the measurement at Mauna Loa for an airborne fraction of 46%. But what a logic! The main inconsistencies of this interpretation are to assume a constant natural cycle and neglection of additional native emissions. This clearly contradicts paleoclimatic and actual observations. Second, one fraction of human emissions is accumulating in the atmosphere over several 100,000 years. The other part is instantaneously absorbed. This is a violation of the equivalence principle. Third, the absorption is considered to be proportional to the emission, not to the concentration. This is in descent to native decay processes at the C14 decay after the Nuclear Testament Treaty. Fourth, the total CO2 content in the atmosphere is exchanged within about 4 years, like in inert gas. So there is no real absorption and emission considered at the surface, only the 54% of new anthropogenic emissions. And fifth, the more elaborate Bern model, also used by the IPCC, considers even 5 different absorption channels, again proportional to the emission, and even worse, working at least partially in series. It contradicts the observed parallel uptake of different reservoirs. So there are different reasons to develop a more realistic approach for the carbon cycle, which considers real emission and absorption processes and which is in agreement with all observations and physical causalities. These studies arose from a close cooperation with the late Murray Selby from Macquarie University, Sydney. He was one of the most renowned scientists in the field of atmospheric physics, and already more than 10 years ago, his work on the carbon cycle has raised significant doubts about the IPCC's explanation. As his studies were not in agreement with the mainstream and in contradiction to his colleagues in Sydney, finally he was released from his professorship. Today this has become the reality. Our approach includes temperature-dependent natural emissions EN and anthropogenic emissions EA over the industrial era. The absorption rate A is proportional to the CO2 concentration C CO2 in the atmosphere and characterized by an effective absorption time tau effective with A as actual concentration over the absorption time. This together as balance gives the conservation law. As the CO2 changes per year, given by the native and anthropogenic emission rates minus the absorption rate. As confirmation of this law and a deeper understanding of increasing CO2, it is worthwhile to look closer to measurements of radiocarbon, which is an ideal tracer for the uptake of atmospheric CO2 by the biosphere and oceans. Carbon 14 is formed in the upper atmosphere by incident cosmic rays when a neutron is colliding with a nitrogen nucleus and kicks out a proton. C14 is rapidly oxidized and has a concentration of about 10 to the minus 10% relative to the stable isotopologs. Its radioactive decay time as E-folding time is more than 8,000 years and thus much longer than our considered observation times. Due to the nuclear bomb tests up to 1963, this concentration was doubled. But with the stop of the nuclear bomb tests, it was possible to measure the uptake by the extraneous reservoirs, typically measured as the C14 anomaly delta C14 as a relative deviation from a reference called the delta per mil value. This is a direct check of the conservation law. As a yellow graph here is plotted the normalized C14 anomaly at Vermont, Switzerland. It is characterized by an exponential decay with seasonal emissions over the first 5 to 6 years due to the reproduction circulation from the stratosphere to the troposphere, particularly at boreal winters. Often these oscillations are neglected, but they give a much deeper insight for the fast absorption behavior. We consider a 3-volume system with the stratosphere as the source of C14. Now, when a mass fraction delta M14 is injected to the troposphere, this increases the mass in the troposphere by the same amount. The concentration in the stratosphere then reduces by delta C14 as the ratio of delta M14 to the total mass in the stratosphere. At the same time increases the tropospheric concentration as the ratio of delta M14 to the mass in the troposphere. But this tropospheric mass is about 10 times larger than that of the stratosphere. Therefore, the tropospheric concentration only changes by 1/10 the ratio of the respective total masses. Something similar happens between the surface and troposphere with a 4 to 10 times larger mass ratio. Solution for the concentrations in the stratosphere, here shown as gray graph, for the troposphere displayed in blue, and for the surface in red, gives good agreement for the troposphere with the observation. It shows a very fast uptake with a direct observation time tau by the surface of only 1 to 2 years, and slows down afterwards with increasing observation to an effective absorption time of 8 years, as this can be seen here by this dashed graph. This effective absorption considers That with increasing C14 concentration in the surface layer, re-emission from the surface to the troposphere can take place, which further limits the uptake. This re-emission is proportional to the actual surface layer concentration and is described by a coupled differential equation system of the three volumes, here only shown for the troposphere. For our further considerations, the surface concentration can be expressed in good approximation as fraction beta of the tropospheric concentration. Then the final decay is determined by the surface concentration and the removal of C14 to the final stores. For tau as 2 years and tau effective 8 years, beta becomes 0.05. So what we find for C14 as tracer also holds for the total CO2 cycle. Applying the same three-volume calculation for anthropogenic emissions over the Mauna Loa era, we can calculate the concentrations caused by anthropogenic emissions, Ca in the stratosphere displayed as orange graph, Ca in the troposphere as blue, and Ca in the surface as red, and how they develop over time. The emission Ea is based on the data of the Carbon Dioxide Information and Analysis Center. Different to C14, the slightly increasing emission occurs continuously and directly in the troposphere. While the troposphere and stratosphere are close to equilibrium, this magnifies the disequilibrium between the troposphere and the surface, and thus inhibits a larger offset of direct absorption by re-emission. This results in effective absorption that can even be faster than the mean decline of C14. This calculation also shows that up to the end of 2023, anthropogenic emissions cannot have contributed more than 13 ppm to the atmospheric concentration, which is just 9% of the CO2 increase over the industrial era, and a further constant emission over successive years can only increase the concentration by 1 additional ppm. This is valid for a tropospheric to surface mass ratio of 1/4. When assuming increased entrainment from the mixed oceanic layer into the deep ocean, or only a larger mixed layer, in the same way as the carbon mass of the extraneous reservoirs are increasing, is the excess mixing ratio Ca of the surface layer decreasing, and with this also the anthropogenic contribution Ca in the troposphere. For a carbon mass ratio of the troposphere to surface layer with Mt to Ms of 1/10, representative for a mixed layer depth of about 100 meters, for example, the respective concentrations are displayed here as dashed graphs. Then the anthropogenic contribution in the troposphere is reducing to Ca of 7.3 ppm, which would be about 5% of the observed CO2 increase over the industrial era, and the effective absorption time almost approaches the direct absorption time. However, with additional native emissions, in average, it cannot be shorter than the total uptake, which is estimated from the atmospheric CO2 concentration and absorption rate as 3.5 to 4 years. So, with an actual anthropogenic emission rate of 4.8% to the total emissions, humans can also only have contributed these 4.8% to the actual CO2 concentration of 420 ppm. How can we explain the much larger increase of CO2 over recent decades? From many observations, we know surface processes like emission and absorption of CO2 depend intrinsically upon the temperature. This is documented, for example, in the seasonal emissions and uptake, almost 6 times larger than anthropogenic emissions. Also in soil respiration, this is found, even increasing exponentially with temperature, or in the emission and uptake by the oceans. Therefore, different to the IPCC, we don't ignore such temperature-dependent processes, not in the biosphere, not in the oceans, or by permafrost. And I would remind to volcanic activities, with about 1 million submarine volcanoes, from which thousands of them are expected to be active. Let us look closer to the CO2 concentration at Mauna Loa as a worldwide reference. The seasonal modulations are obvious, and they are more or less regular from one year to the next, not systematically changing. But what additional emission can be identified over longer time periods? We look closer to the derivative of the deseasonalized concentration CO2 prime, here shown in red, low-pass filtered as average over one season. This gives the well-known conservation law determined by the natural and anthropogenic emissions and their uptake. The difference we call the net emission. This net emission, or derivative of the measured CO2 concentration at Mauna Loa, shows characteristic spikes over 2 to 7 years, which coincide well with El Niño events. And we see a mean increase of the net emission rate with about 2 ppm per year, this over 65 years. On first glance, people may be surprised. This is even less than the anthropogenic emissions, with about 3 ppm per year over this period. But what is plotted here should not be mixed with the direct emission rates, native or anthropogenic, as this here represents the net emission rate, the difference between the total emissions and the absorption. With this net emission in mind, we now look closer to the monthly sea surface temperature record. I have to remind, over mid and high latitudes, there is almost no systematic temperature increase. But in the tropics, as shown in this plot, we see a continuous increase over land and sea, which can well be represented by the sea surface temperature anomaly, and the spikes coincide with El Niños. These are good reasons to explain the observed emissions by an increasing temperature. Here is shown again the net emission at Mauna Loa. Let me make clear, generally these emissions are expected to originate from sea and land, but outgassing of CO2 with temperature from oceans is relatively low, with a temperature sensitivity of only 3% per centigrade. This is more than 1 order of magnitude lower than soil respiration, which is particularly large in tropical areas, where we also observe the largest temperature increase over the last decades. So, when calculating the net emission with the temperature record and soil respiration of tropical areas and considering a slightly exponential increase with temperature, the simulation tracks the observation quite well with a correlation of 80%. Note, the emission is in phase with temperature, while the concentration as integral of the emissions has a phase delay of 90 degrees. This has already been described by Ole Humlum, Kjell Stordal and Jan-Erik Solheim in 2013 and independently by Murray Selby also in 2013. Therefore, CO2, at least for this warming, cannot be the reason for a temperature increase. Finally, to compare the measured CO2 concentration directly with the respective calculation, we have to integrate the total emission consisting of the thermally induced and anthropogenic contributions and also including the seasonal oscillations. The calculation as magenta graph almost exactly tracks the measurement here in blue. The green line represents the natural fraction to the concentration. The light blue graph displays the anthropogenic fraction for a tropospheric to mass ratio of 1 to 4 with the respective values on the right ordinate. As considered earlier, this corresponds to 13 ppm caused by human emissions and is not more than 9% of the increase over the industrial era. And as already mentioned earlier, this is still a conservative value since with this lower mass ratio MT to MS, the effective absorption time approaches the direct absorption time. The anthropogenic emissions, actually with 4.8% of the total flux, is displayed by the lower graph. And we see that for a further constant emission, the concentration is only further increasing by about 10 ppm within less than 1 decade. This is my personal representative concentration pathway. Altogether, the anthropogenic fraction to the total CO2 concentration should be determined by its emission rate to the total emission, which is only about 5%. We find a direct confirmation of the temperature-induced CO2 emissions when looking to the historical data of Ernst Georg Beck. He has collected almost 100,000 historical data about chemical CO2 concentration measurements between 1826 and 1960. These are the first direct measurements of CO2 and thus much more reliable than proxy data. Thanks to Jan-Erik Solheim and Harald Indestad, they were published as post-mortem memorial edition in our journal Science of Climate Change. Respective calculations, only based on thermal emissions and using the same concept as described before, confirm the historical data with a clear peak around 1940. As temperature anomaly for the calculation was used the rural temperature series of Thun and Connolly. So, different to the IPCC, we find human emissions have almost no influence on the CO2 balance, and this already gives a clear answer about our impact on global warming. But I'll also look briefly to the second claim that CO2, human or natural, almost exclusively is responsible for the observed warming. To check also this claim, requires to look closer to the specific features of the atmosphere. This means, on the one hand, we have to consider the incident solar radiation, which is partially absorbed by the greenhouse gases, and on the other hand, what is absorbed from the terrestrial radiation. These absorptions have to be calculated as shortwave and longwave absorptivities specified in percent of the incident radiation, which are both assumed as Planck radiators. But important is also to know what the atmosphere itself is re-radiating from the absorbed power in upward and downward direction, which can be expressed as back-radiated fraction Fa. All this requires radiation transfer calculations for up to 860,000 lines of the gases CO2, water vapor, methane and ozone. This for up to 228 layers due to the changing concentration, pressure and temperature and the propagation path through the atmosphere. This for 14 different CO2 concentrations for different cloud covers and 3 climate zones. The shortwave and longwave absorptivities as well as the back-radiated fraction are displayed as a function of the CO2 concentration, all showing strong saturation which can well be represented by logarithmic curves. These are the key parameters which determine the whole energy and radiation balance of the Earth's atmosphere system as a function of the CO2 impact. For this energy and radiation balance, I use such a two-layer climate model consisting of the Earth's surface and the atmosphere with its sublayers to calculate the influence of an increasing CO2 concentration and also the impact of solar variations on the climate. And different to some lavish atmosphere-ocean general circulation models or the Earth system models, apparently it doesn't fail to prognosticate the actual temperature progression, as I will demonstrate. Additionally to the atmosphere, also the Earth acts as absorber for shortwave and longwave radiation, and at the same time as a source for longwave radiation. At equilibrium, both layers release as much power as they suck up from the Sun and the neighboring layer. This gives a coupled balance equation system which can be solved for the radiated power Pe of the surface and the emitted power Pa of the atmosphere in downward and in upward direction. And with Stefan Boltzmann, the global mean temperatures at the surface Te and of the atmosphere Ta are derived. The key parameters controlling the fluxes are indicated here as red. With this advanced two-layer model, we simulate the influence of a changing CO2 concentration on global warming. The red graph here represents the surface temperature, and the blue graph the atmospheric temperature in about 800-meter altitude. This is a calculation for a mean cloud cover of 66%. These curves directly reflect the strong saturating behavior of CO2 and the overlap particularly with water vapor lines at increasing CO2 concentrations, which at higher concentrations can well be represented by a logarithmic graph here shown as green curve. Doubling the CO2 concentration from 280 to 560 ppm gives the so-called basic equilibrium climate sensitivity as an important parameter to characterize the impact of CO2 on global warming. I get a basic ECS of 1.06 centigrades, which is identical with the coupled model intercomparison project phase 5, also using a different accounting scheme. It is not clear why the new CPM-CMIP6 project is now calculating with a 15% higher value. However, the big differences occur from the feedbacks assumed as amplification of the climate sensitivity and thus the CO2 initiated warming. Well-known feedbacks, as discussed by the IPCC, are the water vapor, the lapse rate, surface, albedo, and cloud feedbacks. Additionally, I consider some phenomena which are even not mentioned in the IPCC assessment reports or in most of the climate literature. These are convection and evaporation feedbacks, and separately from the CO2-initiated effects, we have to consider solar-induced cloud feedback. Altogether, this gives this compilation on the one hand for the CMIP5 and 6 projects, on the other hand for my own calculations with the two-layer climate model at mean cloud cover. This table shall not be discussed in detail, but the yellow fields show the big differences between CMIP5 and 6 and on the other hand my own calculations. The main discrepancies result from the smaller water vapor and the negative evaporation feedback. At mean cloudiness, I get a very moderate ECS of only 0.68 degrees, which is more than 5 times smaller than the CMIP6 value. And there is a principal deficit that the thermally induced cloud feedback cannot explain the observed cloud cover changes measured within the International Satellite Cloud Climatology project. This would result in an unrealistically high ECS between 15 and 18 degrees for the CMIP models. Under my conditions, it would increase to about 1.2 degrees, may be acceptable, but there is another impact which is not considered by the IPCC. Additionally to CO2 radiative forcing, we have also to consider variations in the activity of the Sun, and as we saw previously, this variation also modulates the cloud formation. In active Sun with a stronger magnetic field, reduces the cosmic flux, which is the origin of ion nucleation. With less condensation, we have less clouds and finally also less solar reflectivity. We not only find variations of the solar activity with an 11 years period, but also rather several decades synchronous variations with the AMO and over hundreds of years observed as grand solar minima like Maunder and Spörer minima and also grand solar maxima. These variations are only of the order of 1 or 2 per mil, but they can significantly be amplified by this solar cloud feedback. So, parallel to the CO2 radiative forcing with the different feedbacks, we have the solar forcing with the cloud feedback. Altogether, this can be described by this diagram as a combination of CO2 and solar radiative forcing. I think it is worth noting that on the one hand, the solar anomaly delta TSI is amplified by the induced cloud feedback, and on the other hand, by the same thermal feedbacks as CO2. This scheme is implemented in the two-layer climate model to calculate the simultaneous impacts of the two forcings. The two-layer climate model can also be used to simulate the expected warming as predicted by the CMIP 5 and 6 models, only inserting the respective feedback data. This should work reliably well, all the more the deduced basic ECS was identical with the CMIP 5 value. And finally, these simulations with different TSI time series can be compared with composed land sea surface temperature measurements to derive from this comparison the contribution of CO2 and solar global forcing. Such a simulation with the CMIP 6 data, only assuming CO2-induced warming, already gives an unrealistically high temperature, here represented as magenta graph, when we compare this with the observed temperature measurements shown in blue, which are a combination of rural and sea surface temperature data. Including also solar forcing, even applying an extremely flat increase of the total solar irradiance of only 0.2 per mil over the last 140 years, as reconstructed by Mattis et al., shown in green here, makes it even worse. This TSI series was officially recommended for the CMIP 6 models, surely to limit the natural impact as far as possible and not to further increase the discrepancy to observations. But not only the temperatures since the 50s completely disagree, also the dominant oscillation from 1940 to 80 cannot be reproduced. This we can compare with the simulation based on my calculated ECS value and using the obviously much more realistic TSI series of Hoyt and Shatton with the TSI anomaly of 1.9 per mil. This gives this excellent agreement with the temperature time series, here a composition of data with a weighting of 10% rural and 90% sea surface data. A larger deviation is only found at the end of the 19th century and might be explained by an internal oscillation like the Atlantic multidecadal oscillation. Comparison from 1910 upward gives a correlation of 99% and different to the CMIP simulations can well reproduce the temperature drop around 1970 and also the total temperature increase over the last 140 years. When we finally look to the individual contributions to global warming, we find for a CO2 increase of 82 ppm over the last century and with an equilibrium climate sensitivity of 0.68 degrees, a temperature increase of only 0.24 degrees. For the solar radiative forcing with delta TSI of 1.9 per mil, this gives additional 0.6 degrees. Together, only 0.84 degrees in full agreement with the observation and also with the cloud cover changes according to the International Satellite Cloud Climatology Project. So the sun contributes 70% and the CO2 only 30% to global warming over the last century. Of course, such a simulation is no evidence that the combined CO2 and solar radiative forcing is the only right explanation for the observed global warming, but it clearly shows that the observed temperature time series can much better be reproduced by this stronger solar influence. And even without this impact, the assumed thermal feedbacks of the CMIP 5 and 6 models are too large and have no chance to explain the temperature modulation over the mid-century. So, in summary, our understanding of increasing CO2 is: the carbon cycle is controlled by a first-order absorption process acting equivalently for native and anthropogenic emissions. The effective absorption time cannot be longer than 10 years, but can be as short as 1 year. With anthropogenically caused CO2 of less than 10% and global warming over the industrial era by CO2 of 0.24 degrees, as this follows from the own calculations, humans are responsible for global warming of about 200 degrees. To further reduce this absolutely negligible contribution, we endanger a secure energy supply and with this a prospering economy and stable standard of living. Thank you for your attention.